is coming up, or maybe you're just trying to get your head around what this whole field is actually about, well, you've come to the right place. We are going to do a super fast tour of the entire world of computer science. We're talking from the ground up, the absolute basics, all the way to the global systems we use every single day. And we're going to do it all in about 5 minutes. So think of this as your ultimate high-speed study guide.
Now, for this little tour, we're using a fantastic guide, the Gatopedia for computer science. It just lays everything out so clearly. It's pretty much the perfect map for our journey.
And here's our game plan. We're going to start with the language of logic, see how that's used to build actual machines, then figure out how to give those machines instructions. After that, we'll look at the systems that manage everything, and finally, how we connect it all together. All right, let's jump in.
Okay, first stop, the absolute foundation. You know, before you build a house, you need a blueprint, right? Well, for computers, that blueprint is logic. It's a set of rules that has to be perfectly consistent and predictable. There's just no room for maybe.
This whole language is built on the bedrock of math. We're talking about a kind of logic that deals with simple statements that can only be true or false. And from that, we can build bigger statements that are always true, no matter what. Think of them as the unbreakable laws of this digital universe. They're the fundamental building blocks for literally all computation.
So here's the magic trick, right? How do you get a piece of silicon to think? Well, that's where Boolean algebra comes in. It's this beautiful, simple system using words like and, or, and not. This system is the bridge that lets us take these abstract true, false ideas and turn them into physical on-off switches. It's how we turn a rock into something that can actually compute. Okay, on to our next stop. Now that we've got the language down, we can actually start building the physical machine that can run these operations. We're moving from ideas to actual, tangible stuff. You can think of it like this. Digital logic is all about designing the individual Lego bricks, those tiny circuits that do the math. Then, computer architecture is the instruction manual that shows you how to snap all those bricks together to build the whole castle. You know, the processor, the memory, everything. So it all works together as one big machine.
And this is really where it all comes together. Remember those logical ideas, and, or, not? They aren't just concepts in our head. They are physically built into these tiny electronic switches called logic gates. We combine millions or even billions of these little gates to build the complex circuits that make up the brain of the computer, a brain that can perform any calculation you can imagine.
All right, so we've got a physical machine that understands logic, but right now it's basically a really powerful paperweight until we tell it what to do. So now we've got to learn the art of giving it clear, effective, and really efficient instructions. And that's all an algorithm is. Don't let the word scare you. It's really just a recipe, a fixed set of super precise steps that you follow to solve a problem. It could be anything, from sorting a list of names to finding the fastest route home. You know, studying algorithms isn't just about writing down recipes. It's about becoming a master chef. You have to analyze them to see how fast they are. You learn different design strategies like divide and conquer. And you have to know which recipe to use for which problem, like, say, searching through a giant social network.
Now, a good algorithm totally depends on how you organize your data. We call these things data structures. Take an array, for instance. It's like a fixed-size pillbox, super memory efficient, but you can't just add more slots. A linked list, on the other hand, is like a chain. You can add or remove links anywhere you want, but each link has that extra baggage of connecting to the next one. Choosing the right one is this huge trade-off that can totally make or break your app's performance. Some of the most elegant, really clever algorithms use this concept called recursion. This is where a function solves a problem by calling itself on a smaller piece of the same problem. The whole trick is that it keeps doing this until it hits a base case. A simple version it knows how to solve right away. A classic example is the factorial function. To find the factorial of 5, you just need 5 times the factorial of 4, and you keep going down until you hit 1.
So we've got the hardware, and we've got the instructions. But who's actually conducting this whole orchestra? Well, we need some really powerful software working behind the scenes to manage all of this complexity.
First up is the compiler. Think of it as an expert translator. When you write code, the computer has no idea what you're saying. The compiler's job is to translate it. It starts by breaking your sentences into individual words, or tokens. Then it checks your grammar and makes sure what you wrote actually makes sense. And finally, after a few tricky optimization steps, it turns your elegant code into the raw, brute force instructions that the processor can actually understand.
And then there's the operating system, the real unsung hero of all of this. Your Windows, your Mac OS, your Linux, that's the OS. It's the master manager. It decides which program gets to use the processor, how memory gets divided up, how files are stored. It's the software that makes the hardware actually usable by the rest of us.
Okay, for the final leg of our tour, we're going to zoom way out. A single computer is powerful, for sure, but the modern world isn't built on single computers. It's built on managing insane amounts of data and connecting billions of machines together.
In the world we live in today, managing information is everything. A database management system, or DBMS, is kind of like a super-organized digital librarian for the whole planet. It gives us a structured, incredibly efficient way to store, update, and instantly find huge volumes of data. We're talking everything from your social media feed to global shipping inventories.
And finally, we have computer networks. This is the tech that wires it all together. See, for computers to communicate, they have to speak the same language. We call those shared rules of communication protocols. It's this universal agreement on how to talk to each other that lets a computer in Brazil reliably connect to a server in Japan. And that right there is how you build the internet.
And there you have it. In just a few minutes, we've literally gone from abstract true-false statements all the way up to the global, interconnected network of machines that runs our world. Pretty cool how each layer just builds logically on the one before it.
So we've just laid out the entire map of this incredible field. We've seen logic, algorithms, operating systems, networks. The only question left is, which one of these fascinating territories are you going to dive into and explore first?